Hi all, welcome to new class. Today's class is the continuation of power factor improvement, and today's class is about the problems related to power factor correction. So let us go through the problems. A single phase AC generator supplies the following loads. Lighting load of 20 kilowatt at a unity power factor, induction motor load of 100 kilowatt at power factor 0.707 lagging, a synchronous motor load of 50 kilowatt at a power factor zero point 0.9 leading. Calculate the total kilowatt and kVA delivered by the generator and the power factor at which it works. So here we have to calculate the total kW and kVA. So kW rating it is given. So first of all we can find the total kW. So total kW is equal to 20 plus 100 plus 50, and that is equal to 170 kilowatt. So total kW we have got. Now we have to calculate kVA and power factor. So to find the kVA, first of all we have to find the kVA ratings of each of these loads, and then we have to find the resultant kVA delivered by the generator. And here kW rating we have taken that the sum of these three, because after power factor improvement there will be no change in kW rating. So we can add these three kW ratings, but kVA rating of the generator after power factor correction is not same as that of the sum of these three loads. So we have to calculate first of all the kVA rating of these three loads separately, and then we have to calculate the resultant kVA. So first of all calculate the kVA of the first load. Let it be kVA 1. So what will be kVA 1? So we know kW and power factor. So kW divided by cos phi 1 will be equal to kVA 1. So first one is 20 divided by unity power factor. So 20 kVA. Then kVA 2 is kW divided by second power factor, that is 100 divided by 0.707, and that is equal to 141.4 kVA. Next is kVA 3. So next one 50 kilowatt divided by 0.9, and that is equal to 55.6 kVA. So here we got the values of kVA1, kVA2 and kVA3. Now to find the resultant kVA, we have the equation, that is total kVA is equal to square root of kW square plus kVAR square. So for that we have to find the value of kVAR. So the next step is we have to find the value of kVAR of each load. Now consider the phasor diagram of these loads drawn. So here kW, the first load is at a unity power factor, so there is no angle we have to represent. So next one is at 0.707 lagging, so that kW2 is at an angle phi 2. Then third one is 50 kW at a power factor 0.9 leading, so it is upwards, so and its angle is phi 3. Now let us calculate the values of kVAR for each loss. So first one kVAR1 is equal to kVA1 into sine phi 1. So kVA1 we have got as 20 into sine phi 1 is here. There is no angle, that is phi is 0. So sine 0 is 0. So we got 0. Then kVAR2 equal to kVA2 into sine phi 2. Here we have to put kVA2 as negative because we have to calculate the power factor at which the generator is working. So for that we have to put lagging power factor as negative. So here put minus 141.4 into 0.707 and that is equal to minus 100 kVAR. So here sine phi 2 is negative, so we got minus 100 kVAR. Next calculate kVAR3 and that is equal to kVA3 into sine phi 3 and that is equal to 55.6 into, here sine value is positive, so 0.436 and that is equal to 24.3 kVAR. Now we can calculate the total kVA delivered by the generator. So before that we have to add these kVAR, that is we have to calculate the total kVAR. So total kVAR is equal to, add these three, that is 0 minus 100 plus 24.3 and we get minus 75.7 kVAR. Now we can calculate the kVA delivered by the generator, that is total kVA is equal to square root of kW square plus kVAR square and that is equal to square root of kW, we get 170 square plus minus 75.7 whole square and that is equal to 186 kVA. So the total kVA delivered by the generator is 186 kVA. Now we have to calculate the power factor at which the generator is working. So to calculate the power factor, that is equal to kW, total kW divided by total kVA and that is equal to 170 divided by 186 and we get 0.914 lagging. How we will get it as lagging? Because here kVAR, the total kVAR is negative 75.7 kVAR. So the power factor will be lagging here. So in this way we are calculating the total kVAR, total kW, then total kVA, then power factor. In the case of power factor correction or power factor improvements. Let us do another problem. A 3-phase 5 kW induction motor has a power factor of 0.75 lagging. A bank of capacitors is connected in delta across the supply terminals and power factor raised to 0.9 lagging. Determine the kVAR rating of the capacitors connected in each phase. So here we have to find the kVAR rating of the capacitors. So for that we have the equation leading kVAR, that is leading kVAR is equal to kW into tan phi 1 minus tan phi 2. So for that we have to find the values of tan phi 1 and tan phi 2. So here the first power factor cos phi 1 is given as 0.75. So from this we can calculate tan phi 1. Tan phi 1 is equal to, after calculating the value of phi 1, we can calculate tan phi 1 and we get it as 0.882. Then from cos phi 2, so cos phi 2 is 0.9. So from cos phi 2 we can calculate phi 2, then calculate tan phi 2. Tan phi 2 is equal to 0.484. Now we can calculate the leading kVAR. So leading kVAR by taken by the capacitors is equal to kW into, so kW is given as 5 kW, so 5 into 0.882 minus 0.484 and we get it as 1.99 kVAR. Now we have to calculate the kVA rating of the capacitors connected in each phase. So rating of capacitors connected in each phase is equal to, since this is a 3-phase induction motor, so we have to divide the kVA rating by 3. So we get it as 0.663 kVAR. So the rating of the capacitors connected in each phase is 0.663 kVAR. So that is about the problems related to power factor improvement. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.